Okay, so what's the big picture of what we've been doing? We've been trying to attack one of the problems that I said was one of the major problems in calculus, right, at the get-go, which is if we know how fast something is changing, and we want to know how much of it there is, that's the situation that we're in. Okay? And so we spent a lot of time at the beginning of the semester talking about notions of relative size, and this idea of a constant rate of change. And then we talked about how we could use that to describe little bits of accumulation. Okay? Now, the thing is, though, that we're not always given a constant rate of change relationship, right? So what do we do in that scenario? And that's the process that we're trying to dig into this week, okay? So before we can create accumulation functions from any exact rate of change function, right, which might be a varying function, what we can do is create an approximate rate of change function, okay? And the way we talked about doing that is to partition the x-axis into intervals of length delta x, reassign the x values in a given interval to the x value at the left end of that interval, and then define a step function as a piecewise constant function where the value in each interval is the actual rate at the x value at the left endpoint. Okay? That's what we've been doing. And we're going to analyze this third step today. Okay? Now, just in case, I was trying to explain this to my roommate last night, who's like a fourth-year med student. She hasn't taken calculus in, I don't know, 7 years. And I was trying to explain this concept to her, and I gave her an analogy that we are driving in a car, we're on a trip, and you know, when you get in your car, you start at 0 miles per hour, and you'll eventually accelerate, let's say you're on the freeway, to, we'll be good drivers, 65 miles per hour, okay? But you do that in a gradual way, right? And so if you want to figure out how far you've actually traveled after a certain amount of time, that's not actually the easiest thing to do, right? Because your speed has been changing this whole time. So what we're imagining is instead of keeping track of this gradual change in our speed, what we're imagining is that we've rigged our car to magically go from 0 miles per hour to like 10 miles per hour and set the cruise control there for a little bit of time. And then instantaneously change it so that we're now at a cruise control of 20 miles per hour and have that for some set period of time. And then instantly change to 30 miles per hour for some set period of time. And that's sort of how we're doing it. So rather than having our speedometer go, it's going, right? So, okay, so that's sort of what we're doing. And again, the reason for that is because we've built up these tools where if we're in a constant rate of change scenario, then we can talk about accumulated distance in that example, okay? Okie dokes. So, I've done a lot of talking this week. It's your guys' turn. So, in front of you, you've got a handout, and I want you to go ahead and, so there's a summary of what I just said at the top, and then in bold in the middle it says, let's analyze the process of creating an approximate rate of change function from an exact rate of change function. So I want you to take 2 to 3 minutes to answer questions 1 through 4. And you can talk to your neighbor. You can talk to me. I'm going to walk around. Mark might be walking around if he's mobile. Question, do you not have one? If you walk all night, you need a handout? All right, let's talk about it. So, what is this graph showing on the right? What are the axes? Yes. The x-axis is time. Time in seconds. Whoa. It doesn't say that, but sorry, recollection, right? We had a rocket-powered basketball before. So what other units did we use? We used feet, right? So the vertical axis is, so the information that I gave you in the setup is that this is the basketball's rate of change. When we look at this graph, is this graph the graph of this function? Yes, right? This is the graph of y equals 3x. Okay? So this is the graph of the rate of change function, which means on the vertical axis, what are our outputs? Rate of change, right? And what are the units of that? We just said feet per second. Okay? That's fine. Okay, so then if I want you to represent the ball's rate of change at t equals 4.t, what can you do? T equals 4, did I say 4.t? 4.2, it's Friday. Okay, so how can I represent the ball's rate of change at time 4.2 seconds? Yes. Okay, so r little b of 4.2. Okay. This is the rate of change of the basketball when the time is 4.2 seconds. Okay. How would I compute it? Do I have the ability to compute it? Yes. How do I do it? I have the formula, right? So if I have the definition of this function, so I can actually compute that by doing 3 times 4.2. So that gives me, what, 12.6? What are the units on that? Feet per second. Okay, so this is not the ball's height at 4.2 seconds. This is the ball's rate of change at 4.2 seconds. Okay, so along those same lines, what is the meaning of the ordered pair 2.1, 6.3? Vishay? Beautiful. I'll repeat it because it'll take me too long to write it. So at 2.1 seconds, the rate of change of the ball is 6.3 feet per second. Okay? Now, number 4 is the really interesting question, right? Are we looking at a constant rate of change relationship? So this question was sort of intentionally written vaguely because I wanted you to think really hard. Okay? So when I want to talk about a constant rate of change relationship, what do I need to know in order to be able to talk about a relationship? I need to have 2 things, right? So I need to know what 2 things I'm talking about before I can specify whether or not I have a constant rate of change relationship between those 2 things. Okay? So what 2 things would you like to look at? What 2 things have we been looking at so far? Time and rate of change. Okay? So is there a constant rate of change relationship between the time and the constant rate of and the rate of change? So between time and rate of change. Yeah. Okay. So between time and rate of change, there is a constant rate of change relationship, right? Because for any t value, for any change in time value, right, the corresponding change in t, or rate of change, is 3 times that. Okay. However, if I want to talk about the relationship between time and height, or distance traveled, is that in a constant rate of change relationship? So I see some people shaking their heads no. So do you want to say why? So I think I'm hearing it. So the rate of change of the height with respect to time is given by this graph, right? And this rate of change is not a constant. It's changing, right? At different values of time, the rate of change is a different value. Okay? So this is a changing rate of change. Cool? Ish? Yeah? Okay. All right. Time to attack the second page. Okay? So now, because we've identified that we have a changing rate of change, we want to create an approximate rate of change function for the first 10 seconds of the ball's flight. Okay? What choices do we need to make and what values do we need to define in order to do this? So once again, take a few minutes, talk with your neighbor, and try to get as far down this page as you can. Just this page. Are we ready to talk about it together? Okay. All right. So, again, the big picture idea was I gave you a rate of change function that is changing, right? That's the complicated situation. So this graph is a changing rate of change. So I want to approximate it with a piecewise constant rate of change function. So if I'm going to do that, what choices do I need to make? Yeah? So I need to decide how wide I want my intervals to be. How wide do we want our intervals to be? 2? Okay, 2 seconds. I like it. What else do I need to decide?
Characteristics.
Yes.
Say what choices.
What
you
choice?
used the word characteristics before.
Yeah.
So those two. We need an A. You need to start.
We need a starting value. I need to decide where this whole shebang begins. So where is a good choice for that? 0, right? Starting at -1 would not make much sense. Okay? All right. What else do I need to choose? Am I going to use left end values, right end values, or mid values? What do you want to use? Left? Are there any questions so far? Question?
Like for that A equals 0,
Mm-hmm.
that feels, I don't know, redundant or insinuated by the question saying the first 10 seconds.
It is.
I don't think I would ever think of putting A equals 0.
As a choice?
Yeah.
That's fair for this setting, right? But it is worth noting because, you know, maybe you got distracted for a second, maybe 3, and then you started paying attention. Oh, and now I can observe changes, right? So in that scenario, your starting value would be at 3 seconds, and it would already be at some given height, right? Yeah.
How do you decide, like, to use left, mid, or right?
Toss a coin. I'm serious, right? I mean, and left, mid, and right are completely arbitrary too. We could have chosen the point 1/3 of the way through the interval, or 7/8 of the way through the interval. These are arbitrary decisions that we're making to make our lives easy, okay? But the thing is, once you pick one, you want to stay consistent with it, okay? So that's the key. Okay, so if I make these choices, then when I come over here, I'm going to partition my x-axis into 2-second intervals. So 2, 4, 6, 8, and 10. I'm going to take the left endpoint starting at 0, right? So I started at 0 when I did that. So the first left endpoint is at 0, and the rate of change there is 0. So I assign that rate of change to the entire interval. And then at 2 seconds, the rate of change is 6. I assign that value to the entire interval. At 4 seconds, the rate of change is up here. I assign that value to the entire interval. Okay? And then at 6 seconds, the rate of change is up here. So now I've got that value. And there's another one up higher, but I'm not gonna get to it. Okay? So, but there should be one more, right? For the whole 10 seconds. Is this okay? So once again, the reason for doing this is because we know what to do when we have constant rate of change. This is what makes our life easier. Okay, we can calculate little bits of accumulation once we have this type of relationship. Now let's make sure we understand what it means though. So when t is 3.2, what's the approximate rate of change of the basketball? How do I figure that out? Yeah. You want me to say r of little b of... Oh, you're getting way ahead of me. Let's not work that hard yet. Way ahead of me. So 3.2 seconds is where? Between 3 and 4. I feel really smart right now. That was great. Okay. So 3.2 seconds is about here. Where am I going to look on the graph to find the approximate rate of change? Am I looking at the purple line or am I looking at something I drew? I'm looking at the step that I drew, right? So right here is the point that says at this time value, this y value is my approximate rate of change. Okay? So my approximate rate of change at 3.2 is 6 feet per second. How does that compare to the actual rate of change? Where's the actual rate of change? That's up here, right? There's a big difference between those two. Okay, but we could actually figure out what that value is because we have the function, right? So the actual rate of change is 9.6 feet per second, right? So this is maybe not the best approximation ever, right? How could we improve our approximate rate of change function? Smaller intervals, right? If I have smaller intervals, then maybe I'd have like a little step here, and a little step here, little step here, little step here. So we'd be getting better approximations, okay? So smaller intervals. Okay. Now, we've done the visuals. How do we actually turn all of this into a function? Okay, so now I want to define a function that will do what we've just described using function notation. Okay, so my apologies, they're calculator drool. Okay, the vertical lines, ignore them. Okay, they don't belong there. But the horizontal red lines, what I've done is I've zoomed in and I've given you a sample, right? Your approximate rate of change function might have looked different, but so now let's use this one. Okay, so a sample approximate rate of change function. I want you to tell me what choices I made to create this, and then answer parts B through E, supposing that the current value of x is 2.4. Okay? So go for it. Do I have what? Yeah. Oh, I could do that. Whoops. Yeah. to make sure we get through this today. Whoa. Okay. Are you ready? This is where the magic happens. Okay? So, what choices did I make when I created this graph? From the beginning. What choices did I make? I'm starting at 0. I'm creating intervals of length 1. And I chose to assign the rate of change to the left endpoint. Okay, so there's a red line here, a red line here, et cetera, et cetera. Okay, so now I want to represent those things in this picture. Okay, so if I want to represent my starting value at a is 0, can go ahead and do that like so. Where is delta x represented? The red lines, okay? So I'll make them green because I don't have red. So green here, and this is a delta x, and this is a delta x length, right? These lengths are changes in time, okay? What about this quantity, x minus a? What is that? What is the meaning of that? Distance? Distance of what? Distance per second. Yeah, it's the total distance between our starting value, a, and our current value of x, which is 2.4. So if I wanted to represent x minus a, I would draw this bar all the way across. Okay? So then when we do this computation of x minus a divided by delta x, what is the meaning, or actually, what is it? We can calculate it, right? X is 2.4, a was 0, delta x was 1, so we get 2.4. What's the meaning of that number? It's the number of changes in x. In the time. In which time? You're going to get it. We're going to get it. Yeah. Is 2.4 the number of complete intervals? So I've definitely got one interval, another interval, but then I've only got about this much interval, right? Up to 2.4. So 2.4 isn't giving me the complete number of intervals.
It's like the relative size of the intervals from 8 to x or 0 to 2.4 over the delta x of 2.4 or no, of 1 for each one interval.
Okay, so remember, the meaning of quotient is relative size of this quantity with respect to this quantity, right? So this is the relative size of the length, x minus a, relative to the length of our delta x intervals. So this is saying if I measure in units of delta x, I will get a measure of 2.4 when I actually measure out x minus a. Okay? Now, what happens when I do the floor function to that? What number comes out? 2. What's the meaning of that number?
So like how many times delta x fits in, like how many complete sets of delta x fit in x.
How many? So this is the number of complete intervals, complete delta x intervals that are in this length, x minus a. Okay. So then, oh, that's weird. I don't know how that happened. Okay, but let's see. So then if I wanted to think about this whole sum right here, so I'm taking the number of complete intervals and multiplying them by delta x. and then I'm adding it to my starting value. Where is that gonna, well, what is that? That's 0 plus, this number was 2, right? What we got out of the floor function. Delta x is 1. So it just gives us back 2, okay? So what's the meaning of that value? Here's 2. Why do we care? What is it in relation to 2.4? It's the left endpoint of the interval containing the current value of x. So all of that hard work right there is how we can find the left endpoint of the interval containing the current value of x. Okay, so that's what I summarize here. So if we, for example, had a value of x equals 3.2, then it would reassign us to the value of x equals 3. And it will do this for every value within a given interval. Okay, and so what we've done is we've created a function that will take in an x value and reassign it to the left endpoint of the current value of x. Okay? There's one more page, and we're not going to get to it today. So this just became your homework, okay? So this is going to take you through the process of actually defining the function itself. So just so we're clear, all we've done so far is reassign current x values to left endpoint x values. We have not defined the approximate rate of change function yet, okay? So we still have to do that, and that's what this last page is about, okay? Do it carefully, and look on Blackboard for modifications to what's going to be on quiz 4, because we didn't get as far as I wanted to, and your homework for the weekend, okay?
I missed attendance.
I didn't take attendance,
Oh, okay.
so you didn't miss it.
Good time.
Mm-hmm.
Thank you.
No problem.